at Novo Nordisk. Go ahead, Claus.
Yes, thank you very much. And thank you for giving me the opportunity to speak at the R and Pharma conference. I'm speaking on behalf of this team of speakers you can see down here, all from Novo Nordisk. And I have a standard disclaimer that the views and opinions expressed are those of the speaker and not necessarily Novo Nordisk. Let's start by imagining a randomized clinical trial, parallel arm, 4 treatment arms. We have a placebo group and 3 treatments, maybe 3 different doses of the same compound. It's a double-blind trial. Randomization is stratified by region and so on. And that is kind of a standard trial that we're doing. We're going to look at the treatment differences of each of the treatment arms versus placebo. And we have a key endpoint that is a parameter y, where we calculate the percent change from baseline to end of treatment, and we want to analyze that. We want to use a treatment policy estimate where we analyze using a covariance analysis of covariance, where we put in treatment and region as factors, and then we put in the baseline y as a covariate, allowing for different variation in the treatment arms. If we have missing end of treatment data, then we want to impute those values using multiple imputations. And we do that by looking into imputation groups that are defined by the treatment arm, and then also if the participant is on or off treatment when they come to end of treatment. So if a participant stops the treatment during the trial, he is encouraged to stay in the trial and have all measurements taken anyway, and we will use all those measurements. But anyway, if they have missing end of treatment data, we will impute based on the 8 groups that are then defined by the treatment and then on-off status. You can see a box plot on the right-hand side on the end of treatment observations for the treatment arms, and in this case, this y parameter, it is good to lower it, so the percentage change should be lowered. That's good for the patients. I have simulated data from these parameters you see here. So placebo on average has a mean percentage decrease of 5. Treatment A will lower in the mean by 50 percentage points, and B will lower with 40, and C will lower with 25 percentage points. And you can see other parameters here, for example, how many are missing and how many go off treatment during the trial. For the participants who discontinue treatment before they reach the end of treatment, I have simulated so that they lose half of the effect they have achieved, would have achieved if they stayed on treatment. And then I've randomly introduced about 10% missing that have missing data. And our mission is to have the opportunity to both use SAS and R depending on your expertise or the problem at hand, so that you can use them interchangeably within Novo Nordisk, and let it be independent of the program language to conduct the analysis and also the review. Typically, we would have one that programs the analysis and another one that independently also programs the analysis, and then they match the results and see if they agree. And we would like that to be independent of the programming language. So I put up the essential SAS code for the statistical analysis. So essentially we use the PROC MI to impute the data, PROC mixed to estimate all the parameters, and then the MIANALYZE to use the Rubin's rules to combine all the imputed analysis. And I've hidden a lot of details. One thing that you notice here is on the right-hand side, I've put in an option here called EDF equals 687. So that is to match the implementation in R, because SAS has not implemented a correction to the degrees of freedom in the Rubin's rules that was published in Barnard and Rubin in 1999. But you have a possibility for manually changing that, so you would get the same as R in this case. I also have the essential R code for the statistical analysis here. We use the mice package and together with the mice adds package so that we can impute within these treatment groups defined by the treatment and the status. And then we fit using GLS to allow for different variation for the treatments, and we use the pool function to use Rubin's rules to combine the results. Here you see the results. We have treatment A, B, and C stacked on top of each other, the treatment difference with placebo. The programming language R is in red and SAS is in the bluish color. And then for 4 different number of imputations that's done, starting from the top, the small, only 5 imputations, and going up to 5,000 imputations. The dotted lines, they are if I fit the models using complete data, so before introducing missing measurements. So sort of the truth. And you can see that actually R and SAS, they agree a lot. I'll come back to the differences later. So to compare, if I use the same imputed numbers, so I could generate imputed data sets in SAS and export them to R, and then analyze them using GLS, and also analyze them in SAS using PROC mixed, then I could get very similar results. There's something about the degrees of freedom which may impact small samples, but they more or less agree there. If I again use the same imputed data sets, then I can get, using Rubin's rules, exactly the same if I implement this adjusted degrees of freedom in the SAS function. But I have a problem with the random number generators. Both use a Mason-Twister algorithm as a default, but I can't get them to make the same random numbers with the same seed. So it means that I'm not able to reproduce the imputed values from SAS, and that gives some differences in the results. But increasing the number of imputations does not always yield results that gets closer between R and SAS. But if I then change the seed, both in R and SAS, then it seems that the differences are within the variation of changing those seeds. So I think we are good here. So the final recommendation is either, there are 2 approaches. So one is if you really want to get the same, exactly the same, then you need to specify in tedious details in the statistical analysis plan, both the seed and the sorting of the data sets, the number of imputations, and also the programming language in order to be able to reproduce it perfectly. But if you're satisfied with a more pragmatic approach, then you can pre-specify more high level, and that's where we are going, and then carefully evaluate the impact of changing seed and the number of imputations and so on, and then report if the results are not robust. I think, of course, you should also do this by establishing the robustness of the results in the approach number 1. And that's all I have. Thank you.
All right, Claus, thank you so much. Does anyone have any questions in the chat? Can they add some questions in the panel? Anyone?
And I will, of course, share the slides.
Yep. You'll have the slides afterwards, right, Claus? You'll be able to share along the slides at the end?
Yes.
Great. Okay, so thank you very much. We have